Hello everyone, this is our first lesson from Unit 3. We are going to talk about rational exponents and complex numbers in this unit. A lot of interesting math is going to happen, and part of what we need to do is do a little bit of review on some of the properties of exponents that you might remember from previous math classes. Okay, so let's start with the basics. Um, First off, what is an exponent? An exponent is repeated multiplication, right? So we know that 2 times 2 times 2 can be rewritten as 2 to the third. And that's notation that's been in existence for hundreds of years. And one of the things about how math has developed over the course of hundreds, thousands of years is people have found easy ways to write tedious calculations. And that's a lot of times how math notation gets developed. So when we had originally, it was, years even before that, where we had, say, 2 plus 2 plus 2 plus 2, and we wrote that as 2 times 4. So knowing that notation and how multiplication became a shortcut for addition, we were then able to look at that and say, oh, well, this new operation that's called multiplication, it has properties like that notation, um, which represents repeated addition. It has certain patterns that occur to it, like certain additions will lead to certain multiplications. And the same is true for exponents. So knowing that 2 times 2 times 2 is 2 to the third, um, 2 times 2 times 2 times 2 is 2 with an exponent of 4, and so on and so forth. So in this case, we look at different reasonings behind the notation and how the notation in different problems works together to create a full list of different tools, tricks, and shortcuts that we can use to represent all these different multiplications. Um, so this notation has its own properties. Um, so let's take a look, shall we? Okay, so our first major objective here for this lesson is we're just looking at evaluating expressions with integer exponents. Again, this is simply, in many cases, a review of things that we already know. Um, so later on in future lessons, we're going to look at what happens when you don't have integers, or can we, since we know the patterns that exist for some exponents, and for integer exponents, could those properties be extended to other kinds of numbers? And we're going to take a look at all of that. So let's start with this big chart here. So there's lots of different properties that exist for um, product rule, quotient rule, power rule, and exponents have all sorts of patterns, as we said before, that um, that govern good shortcut ways to write everything. So um, let's start with our first example. Let's say we had um, two things that are multiplied together. Let's say we had 2 to the third times 2 to the fourth. And we wanted to, figure out like what that might equal. So if we look at, the breakdown of this, right? Remember what an exponent is. An exponent is repeated multiplication. It is a shortcut for an operation that we already know. So in this particular case, that operation being multiplication, we can expand it out, right? So 2 times 2 times 2 times 2 times 2 times 2 times 2. So let's think about what's going to happen here. So we're multiplying in the middle, these terms, but these terms also have multiply in them, right? is these multiplication dots, are they any different than these multiplication dots? No, they're not. It's all multiplication. Multiplication is multiplication. Yeah, well, until you get to like linear algebra and matrix theory and yuck. Yeah, I'll save that for another time. Multiplication is multiplication, right? Between numbers, at least. So we don't even need the parentheses here. And we can just simply write this as 2 times 2 times 2 times 2 times 2 times 2 times 2. And we can write all that out. And so what we have is 2 to the 7th. We have 3 2's multiplied together, 4 2's multiplied together. That gives us 7 2's multiplied all together. As a general rule, we can write it as a to the m times a to the n equals a to the m plus n. And so the big idea is that if you have two like numbers that have exponents and they are multiplied together, then the exponents get added. But remember, this only happens if the bases are the same. If you had, say, 2 to the third and 3 to the fourth, then what you'd have is you'd have 2, 2, 2, 3, 3, 3, 3. And while you could write it without the parentheses, it wouldn't combine at all because the 2 and the 3 don't really do anything. Okay, what about quotient rule? What would happen in terms of the quotient rule? Well, let's see. Quotient rule, well, quotient involves division, right? So what about division? If we have um, multiply, right? We multiply terms with exponents together, and that causes the exponents to be added. So what happens if I change this to division? If I did, say, 2 to the 7th divided by 2 to the 4th. Well, we already know that division is just the opposite of multiplication, right? So if I start with 2 to the 7th, and I'm dividing away 2 to the 4th, shouldn't I be left with the other factor of 2 to the 3rd? I should. Now, why does that work? Does it mean we subtract exponents? So 2 times 2 times 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2 times 2. Okay, so 7 2's divided by 4 2's. Well, remember, when we're dealing with a fraction, we can always simplify a fraction by crossing out like factors, right? So I can cross out like factors. So when I do this, I cross out 4 from the bottom, 4 from the top. I know I said that backwards. Let me just erase them. Gone and gone. What am I left with? I'm left with 2, 2, and 2. I'm just left with 2 to the third. So by dividing, I've subtracted 4 of the factors. And so now this rule, in the general form, is a to the n divided by a to the n is equal to a to the m minus n. Okay, so multiplication turns into addition of exponents. Division of terms becomes subtraction of exponents. Well, that's pretty convenient. And it turns out this is one of the reasons why exponents were created centuries ago, was a way to convert multiplication and division problems into addition and subtraction problems. Why would we want to do that? Because addition and subtraction is a far, far easier operation to perform on paper. Okay, now we have some other rules that are really good ones to know for our work coming up. The next one's called the power rule. So with the power rule, this happens when you have multiple exponents attached to the same base. So let's say you had, instead of multiply, what if you had this? 2 to the third to the fourth power like this. What would that be? Well, let's see. If I were to write this out now, when something is to the fourth power, this term is multiplied by itself repeatedly, right? 2 to the third times 2 to the third times 2 to the third times 2 to the third. Well, now it looks like a product rule problem, doesn't it? And I have 3 plus 3 plus 3 plus 3. And I can add all that together and I get 2 to the 12th. But 3 times 4 is 12, right? I have 4 copies of 3. That certainly sounds like 4 times 3 to me. And sure enough, that's the actual rule. So the rule for this, and I'll write it over here, is a to the m to the n power is equal to a to the mn power. Now, this is important. Why is it that in this problem we multiply the exponents together, where in the original product rule we add the exponents together? Visually, what is the difference? Notice for the product rule, I have 2 separate bases with 2 separate exponents and a forced multiply in between. So 2 to the third times 2 to the fourth. Now look at the power rule. Power rule, the big thing to think about here is the fact that you have parentheses. Power rule only really happens when you have something that is grouped in parentheses because it has to have one single base, and that single base has to have 2 exponents, one on top of another. So it's 2 to the third and then that to the fourth. So that would tell us that these exponents get multiplied. Okay. Now, one thing I will say that this is not, and another common mistake that I sometimes see, is people see 2 to the third to the fourth, and they'll think of it as this, as 2 to the third to the fourth. That's totally different. If you see this, sometimes this is called a power tower. Um, you actually evaluate it from the top down, not the bottom up. If you were to evaluate this um, from the bottom up, you get like 8 to the fourth power, or you might actually get 2 to the 12th. But instead, this is 2 to the 81st, because 3 to the fourth power is 81. That's not what this is saying. So we're going to get rid of that. No, we're not going to need this. That's not the power rule. So I'm just going to go ahead and erase it. Okay. Next rule, power of a product rule. All right, so power of a product, this is what happens when you have the power rule, but multiple things in the parentheses. So like, for example, if you have, say, you have 2x to the third raised to, say, the third power. Okay. And you might have seen expressions like this in the previous units where we've had, terms with x's raised to extra powers. So what happens in this case? Well, it looks like we do have a power rule here because you have the 3 exponent and then another 3. So it looks like those exponents get multiplied. Sure enough, they do. But just to be safe, let's write it out like we did up here, and we get 2x to the third times 2x to the third times 2x to the third. Sure enough, we do get the 3, 6, 9. We do get x to the 9. But what we also get is the fact that we get this 2, 2, and 2, we get this 2 to the third power as well. And 2 to the third is small enough that we can just rewrite it as 8. So in this particular case, I like to also call this, the distributive property, if you will, of exponents. Distribution of exponents because it turns out exponents distribute across multiplication. So if you have a term that is comprised of factors, like multiple factors, and that whole factor has been raised to some power, then that power can distribute across all the factors. Um, However, it stops at multiplication and division, or sorry, addition and subtraction. It stops when it gets to addition and subtraction. So exponents do not transfer across multiplication, sorry, addition and subtraction. We're just dealing with multiply and divide usually in this unit, right? So in other words, if I have this term, and I'll put this down here at the bottom of it. So this is another common thing that I see is if I have the term, say, 2 to the third plus 3 to the fourth squared, okay? This is not equal to 2 to the sixth plus 3 to the eighth. Bad, bad, bad. Don't do that. Bad. I'm crying. I don't ever want to see that, please. That is not mathematically correct because exponents will only transfer across multiplication. So if I had 2 to the third times 3 to the fourth squared, now that's equal to 2 to the sixth times 3 to the eighth. And that one does work. So definitely understand the difference between those two. A good way to think about it is exponents are defined using multiplication and division. So it makes sense that their definition only carries across those two operations. Okay, we have two rules left to cover. Negative exponents and zero exponents. All right. So what is an exponent? I ask that question again. An exponent is a shortcut for repeated multiplication, right? So knowing that you have, say, 3 to the fifth, we know that that's 5 threes all multiplied together. 3 times 3 times 3 times 3 times 3. That's, 5 factors of 3. All the way down to 3 squared, which is 3 times 3. What's 3 to the first? Well, should be 3, right? If 3 to the first means I've got a single factor of 3, it's not one multiplication, but it's a single factor of 3. So that means that 3 to the first is 3. 2 to the first is 2. And in general, this leads us to the basic property that anything to the first power is equal to itself. So let's go back for a second and now let us think about what happens if we extend this pattern. So let's go back here and let's write some things out. I'm going to change this from 3 to the fifth. We're going to make this 3 to the third. So 3 to the third is 3 times 3, and that's 27. And 3 squared is 9, and 3 to the first is 3, right? So normally, when we increase an exponent, we multiply by 3, right? So like the next one would be 81, then 243, and so on and so forth. So multiplying by successive 3's increases the exponent. Wouldn't it be true that decreasing the exponent happens when we divide? Take a look at this. If we go from 3 to the third to 3 squared, aren't we dividing by 3? And then if we are dividing by 3 again to get to 3 to the first, then what about 3 to the 0? What if I have no 3's? no 3's being multiplied together. I have no factors. Well, if I reason that, the answer would be 0. Except, think about this. If I follow this pattern, then logically the next step would be to divide by 3, right? To get the exponent to go down one more. Well, what's 3 divided by 3? 1. So 3 to the 0 power is 1. Likewise, 2 to the 0 power would be 1, so on and so forth. Here's another way to look at it. Suppose you had, say, some term here, like 2 to the 6th, right? And we wanted to reduce this exponent, right? Well, what operations do I know that reduce exponents? Let's see. Subtraction. Okay. So look at the quotient rule here. 2 to the 7th divided by 2 to the 4th is equal to 2 to the 3rd. So could I divide this by something to get to 2 to the 0? What would I have to divide it by? I'd have to divide it by 2 to the 6th, right? Because 2 to the 6 minus 6 is equal to 2 to the 0. And what's any term divided by itself? 1. Any number divided by itself is 1. And you could try, I mean, this is, 64 divided by 64. But that's true for any power. So 0 exponent property, any number to the 0 power is equal to 1. As long as a itself is not 0. Because then what happens if you have 0 to the 0? What happens if I tried replacing all of these with zeros? What would happen? I would have, let's erase it. I would have what? 0 to the 0? Actually, I'll leave it there. I won't bother writing that. I'd have 0 times 0 times 0 is 0. 0 times 0 is 0. That would be a 0. But then this would be a 1. But I'd be dividing by 0 each time. But I can't divide by 0. So this argument makes no sense. What if I tried that over here? I had 0 to the 5th divided by 0 to the 5th would equal to 0 to the 0. But then 0 to the 0 is equal to 0 divided by 0? I've said the word 0 too many times. Let's not think about that. That is something called an indeterminate form. So 0, I'll just write this down here. 0 to the 0 is called indeterminate, which means it has a value for which we cannot assign or find a true value for it. It could potentially be, lots of different values. And so it doesn't really, there's no way using the math that we know to write a value for it. And so therefore, it can take on pretty much anything, and it doesn't give us any information as to what the value actually is. So this comes up a lot in calculus, where if you get an expression that simplifies to say 0 divided by 0, it doesn't tell us anything, and then we have to try solving the problem a different way. Okay, so this a is not equal to 0. That's got to stay. But that's true for anything. So like, as long as a is not 0. So if I have, say, 5 to the 0, that's equal to 1. And the best logic, the easiest way I can write it here is this argument right here, where if I have, say, 5 to the 6th divided by 5 to the 6th equals 5 to the 6 minus 6, that's 5 to the 0, but anything divided by itself is just 1. So what happens with negative exponents then? What happens if this pattern keeps going? 3 to the negative 1. Could I keep dividing by 3? What would the next term be? 1/3. And the term after that? What's 1/3 divided by 3? 1/3 divided by 3 is equal to 1/3 times 1/3, which is 1/9. And then every time I divide by 3, it's the same as multiplying by 1/3. So that's just going to keep growing by factors of 3 in the denominator. So, oops, that's not what I wanted. Does this pattern hold? Look at this. 3 to the third is 27. 3 to the negative third, 1/27. 3 squared is 9. 3 to the negative 2, 1/9. Does that pattern hold? Let's find out. Let's go over here. I'll erase this part of our work that we did here. Okay, I tried to do a fancy move. That didn't really work. There we go. All right. Okay, so let's say I had 2, let's look at a problem we did before. 2 to the 7th over 2 to the 4th. We know that's 2 to the 3rd, right? And we know that that's 8. And we knew that because we had the 2's before. But what if I reverse these two? And I did 2 to the 4th divided by 2 to the 7th. What would happen? Well, I would get, according to the quotient rule, I'd get 2 to the negative 3rd. 4 minus 7 is negative 3. But what is that? If we were to write it out, we'd get 2 times 2 times 2 times 2 over 2, 2, 2, 2, 2, 2, 2. And what would happen? These 2's would cross out with these 2's, but look at where the remaining 2's are. We still get 2 to the 3rd power, but it's in the denominator. We get 1 over 2 to the 3rd, or 1/8. So it certainly sounds like that this is a pattern that would hold. And we can fill in that rule up here. Is that some number like 2 to the 5th is equal to 1 over, or sorry, 2 to the negative 5th is equal to 1 over 2 to the 5th. The general rule is that a to the m or a to the negative m is equal to 1 over a to the positive m. Notice that means that negative exponents still give positive answers. And the reason for that is what we did before. And that was, I'll just write it here, 2 to the 7th divided by 2 to the 4th equals 2 to the 3rd versus 2 to the 4th divided by 2 to the 7th is equal to 2 to the negative 3rd. And so the negative exponent rule is basically just a continuation of the quotient rule. Okay. But there's all your rules for you. And all those rules kind of come together to form all the different properties and things that we should know. So it can be a lot to take in at first. But remember, one of the things that I made have mentioned in class is that knowing the rule is half the battle. Understanding why the rule is there is the other half. And that's what I hope to try to show you here. It's the same argument that we can make about speed limits. So you're driving down the road, and the road has a speed limit of 40. Now, you may think to yourself, okay, I understand that the speed limit is 40, and you might drive at 40 miles an hour. But what if you don't know why the speed limit is 40 miles an hour? Now, we all know like the general reason for speed limits, right? Can't drive too fast, may not react in time, things like that. But we're talking about maybe like specific roads. Like you have a road that travels that you travel all the time. You may wonder, why is the speed limit 40 miles an hour? Or you may have a speed limit that you may not agree with, right? Why is the speed limit 40 miles an hour on this road? But if you understand, if you travel the road enough and you understand, oh, later on there are some curves, there's some blind spots where you can't be going too fast, despite the fact that this section looks pretty open, then you start to get an understanding. And once you understand why that speed limit is 40 miles an hour, you are far more likely to follow it. If you've ever driven on a road that's straight as an arrow, like we have one where I live, there's a road, it's straight as an arrow. The speed limit is 25 miles an hour. And it doesn't feel like the speed limit should be 25. It easily looks like feels like a 40 mile an hour road. But there are several reasons why that speed limit is 25 miles an hour. Um, and it was only after driving that road every day for a few years that I started to understand why. It has to do with the fact that the road is a shortcut. Cops were trying to dissuade tractor trailers from using the road as a shortcut, and that among many other things. And high rate of accidents, pedestrians getting struck, things like that. And once I understood those things, then it became much clearer and much easier to keep to 25 miles an hour. The same thing happens with exponent rules. The more you understand why the rule is, why we add exponents, why we subtract exponents, why we multiply exponents in the situations that we do, the far easier it is to just do them and to know to do them because you understand the why. So just a little bit of practice here. Just to end here, we'll just do a couple questions just to make sure that you kind of have the sense of what I'm trying to say here. So like knowing that, say, if you have, say, 2 to the third times 2 to the x equals 2 to the eighth, like what does that tell you about x? That tells you that, x must be 5, right? Because 3 plus 5 is 8. I have 3 twos, and I multiply 5 twos, and I get 8 twos. Or simply knowing that, like, 3 to the 10th divided by 3 to the 8th, and know that that's 3 squared. And remember, we even did problems like that before, where, like, when we had x's, right? And remember where we did long division, and we had, say, x to the third divided by x. That's not 3, that's x squared. And why is that x squared? Because this x is x to the first. So 3 minus 1 gives us 2. Now we kind of understand that. Okay. So just knowing that in a division question, exponents get subtracted like this makes it far easier when we have the long division situations and you're dividing x to the third by x and you realize, oh yeah, it's got to be x squared. Does that make sense, I hope? Um, but then also things like negative exponents, right? So when you have something like, if I have 4 to the 6th divided by 4 to the ninth, okay, I have more 4s on the bottom. So I have two ways of writing this. I can either say that 6 minus 9 is the negative third, or I could say that if I cancel out 6 fours and 6 fours, I'm going to be left with 3 fours, but they're going to be in the denominator, 1 over 4 to the third. Both ways are equivalent in terms of writing. Um, And you'll see things written both ways, both with positive exponents and with negative exponents. And it's important to understand that these two here, these two expressions, are equivalent and interchangeable. So little things like that. Um, there is one situation that can also come up too. Uh, sorry, I just picked up my. I have a cup of tea, and I just picked it up and found two ladybugs in it. Oh, lovely. Ah, well. Anyway, there's one more situation, I guess, ladybugs notwithstanding, that you could find yourselves in. Um, and let's say you had a question like this. You had, say, 3 to the fifth multiplied by 9 squared. Now, at first, what would you do with this? It's like, okay, well, nothing, right? The 3 and the 9 are separate bases. And we've already mentioned you can't combine things with separate bases. However, sometimes you can combine terms where one base is a power of another. Like, look at 9. Isn't 9 equal to 3 times 3? So here's a case where if you rewrite this, 3 to the fifth times 3 squared squared. Because the 9 is 3 squared. Now what you have is you have a product of power, which means powers get multiplied. And this is equal to 3 to the fifth times 3 to the fourth. 2 times 2 is 4. And now these get added to make 3 to the ninth. Now, this only worked in this one case because we had 3 and 9. Like if you had 2 and 4, yes. 2 and 8, yes, because they're powers. But if I had, say, just remember that, like if I had, say, 5 squared times 7 to the third, that's just, it is what it is. We're not going to be able to simplify that anymore. Um, just keep in mind, sometimes some bases can't be simplified. Okay, guys, that's just a few examples, kind of how we might use these powers. That's about it for that. I think I'm gonna go make myself a fresh cup of tea now. Oh well. Have yourselves a lovely night, folks.